Hi. In this segment, we shall look at the next type of discrete structure, trees. Trees are special kinds of graphs, a subclass of graphs, if you will, distinguished by particular structural properties. They generally look like this graph here. This kind of structure naturally lends itself to representing hierarchical relations. Hierarchical groupings of things such as file systems and domain names can be arranged in this way, for example. The definition of a tree is that it be a graph defined by its vertices and edges as before, although the conventional placeholder names are no longer V and E but T and R, yet otherwise they remain the same thing. For a graph to be a tree, it must have the following properties. If it not be empty, it contains a vertex, let's call it A, such that for every other vertex, there is exactly one path that starts at A and ends at the other vertex. Also, there is no path from A to itself. A little bit of special terminology applies to naming the different parts of a tree. Instead of vertices, people often use the term node when talking about graphs that are trees. The special node A, from which there is only one path to every other node, is called the root of the tree. Unlike most of their botanical colleagues, computer science trees tend to grow downward from their root. However, they do also have leaves, which are nodes from which no links go to any other nodes. A link is the tree word for edges. And they go downward from the parent node to the child node. The special structure of trees results in some interesting properties. First, the first is that the root is unique, so there cannot be two of those special nodes A with a unique path to every other node. Also, every node that is not the root has exactly one parent, while the root has none. The tree with n nodes contains n-1 links, and it cannot have any cycles. The fact that an n-node tree has n-1 links also implies that trees are minimal connected graphs. A connected graph is one that hangs together, so there are not several isolated groups of nodes or vertices that have no connection between them. It is minimally so if it becomes unconnected if you remove any one of its edges. Even though trees are minimal connected graphs, the reverse is not true. Not every connected graph with a minimal number of edges, that is n-1 for n vertices, is also a tree. Try to construct one that isn't. It only takes 3 vertices and 2 edges. Given a tree, we can group its nodes by their distance from the root. We measure that distance either as link height or level, which is the number of links one has to cross on the path from the root to a node, or as node height, which counts the number of vertices in the path from the root to a given node. The highest node height of any node in the tree is also the overall height of the tree. As for graphs in general, trees are everywhere in computer science and other disciplines. Grammar trees, for example, represent the syntactic structure of expressions in natural and artificial languages, including, of course, importantly, programming languages. Game trees represent various positions of some game and the moves between them. In biology, the taxonomy of all life represents the relationships between species, or perhaps more accurately, our current best knowledge of these relationships. In many applications, trees are used to structure information that is attached to their nodes. For this purpose, we use so-called labeling functions that map the set of nodes to some set of quote-unquote labels. The word label should not imply that they're always strings. They may in fact be anything that we might want to attach to nodes arranged in a tree. Also, keep in mind that even though we use a function to represent the connection between nodes and their data, in practice data structures representing the tree would often just directly add it to the data structure representing the node. Looking at this labeled tree, and suppose it is intended to represent an expression, what expression might that be? Well, this one. But does it actually represent this expression? It's important to understand that it doesn't represent it uniquely. Keep in mind that this visual representation of the label tree is just that, a visual representation. In this case, the placement of the nodes suggests information that neither the tree itself nor the labeling actually provides, that of an order among the child nodes of a node. The tree doesn't have one, even if the graphical representation suggests otherwise. That is why we need order trees. When the order among children matters, as it does typically with trees representing syntax, for example, we need to add a little more information to them. This can be done using a function like mu, which maps all non-root nodes to a natural number so that the n children of each node are numbered 1 through n. So with the numbering as in the mu in the example, the expression syntax tree could be made to uniquely represent one particular expression. Note that by convention, the order in order trees is often visually just represented implicitly through the left to right arrangement of the child nodes. This means that there is no visual distinction between unordered trees that just happen to be laid out in a particular way, and ordered trees where the arrangement carries meaning. To make sure, when you represent trees in this way, tell the reader or listener how to interpret your visuals. Another common type of tree is the binary tree. In it, every node has at most 2 children, and the labeling function labels them with one of 2 labels, typically something like left and right, such that no 2 children of the same parent are ever labeled the same. As is the case with ordered trees, the visual representation of leftness and rightness of children usually happens through placing them left or right of the parent node. This again makes it impossible to know whether the child placement carries meaning or not by just looking at the graph. So again, make sure you communicate this unambiguously when you use this kind of representation in your writing or in a presentation. A very common type of tree actually combines being a binary tree with being labeled. Suppose the label set is totally ordered. For example, by the alphabetical order on strings representing names or numbers. The idea is that the structure of the tree can be used to arrange the labels in the tree in a way that makes it faster to search for them. We call a binary tree a binary search tree if for every node all the labels in its left subtree, the one starting with its left child and going down from there, are less than its own label, and all the labels in its right subtree are greater than its own, as is the case in this example. But why do we actually need to distinguish binary trees to begin with? Couldn't the same be achieved by ordered trees? Aren't binary trees, in other words, just ordered trees where you only count up to 2 children? Or are binary trees something different? The answer is that binary trees are indeed different. The reason is that the numbering on an ordered tree establishes a total order among the children only, while the left-right labels on a binary tree also relate the children to their parent node.